Hi, and welcome to week 5 of Introduction to Meteorology. I'm Deke Arndt. We haven't met by video yet because this is my first week to do this, so I may not be very good at this, so please be patient with me. Week 5 is a pivotal week because it has a lot to do with atmospheric stability, how the atmosphere can arrange itself vertically, and whether that can support heavy precipitation or not. So it really is a critical week. Stability, if you're someone that took this course because you have a real interest in severe weather, this is one of the key concepts in severe weather, is how unstable or stable the atmosphere is, and a good chunk of chapter 5 is dedicated to the concepts of stability. The main driving factor in stability, at least the type of stability we're talking about in this chapter, is how rapidly the atmosphere cools as you go up. There are a lot of subtleties, and students that go through a meteorology degree program have to learn a lot of subtleties, but this type of instability or stability is very much to do with how rapidly the atmosphere cools as you go up. And the reason that comes into play is because a stable atmosphere is one that supports, if a parcel rises, it's going to be heavier than its environment as it goes up and come right back down. In an unstable atmosphere, as a parcel goes up, it's going to be lighter than its environment and continue to accelerate upward, and that's what drives and fuels big thunderstorms. So what makes a parcel warmer or cooler than its environment as it goes up has a lot to do with the environment as it goes up, and that's what stability is all about. If the atmosphere cools very rapidly as it goes up, that parcel won't cool as quickly as the atmosphere as it goes up, and it will be relatively not cooling as rapidly as the atmosphere as it goes up. And then that means at some point it's going to become warmer and less dense than the environment around it. Just like a hot air balloon. You heat that sucker up and it's going to go up. That's the driving force, the buoyancy, the difference in the density between the air inside that hot air balloon and the environment around it. That's what instability is. If you create an atmosphere where as you go up it gets very cold aloft, as you take that parcel or hot air balloon or whatever piece of air you're thinking about and you put that in a very cold environment, well, chances are it's going to be quite warm compared to the air around it, which is going to propel it upward even more. So it's an important concept, instability. Again, stability, a stable atmosphere is, as a parcel goes up, it's going to be colder than its environment, it's going to come right back down. In an unstable environment, as a parcel goes up, it's going to be warmer than its very cold environment and continue to accelerate upward. And it's that force, that's the updraft that we see in big thunderstorms. And so large thunderstorms that have powerful updrafts and support large hail, those occur in a very unstable environment or an atmosphere that cools very rapidly as you go up. One other concept kind of to slice stability up a little bit are the 3 categories of stability that are defined in the chapter. A stable atmosphere, a conditionally unstable atmosphere, and an absolutely unstable atmosphere. And there's differences in those. It's important to give that section a good read. All right. One thing I wanted to go over is the wind roses, and this is very low tech, and I apologize, but we had an assignment, and we're going to build on that map assignment that had a bunch of wind categories. And so most of you did well, but I want to reinforce some things just to make sure that the same misinterpretations don't catch you all semester. So here is a standard wind barb, and I'm sorry I'm not used to being on camera. This demonstrates a wind. Some points here. This is a station plot, and in this plot it's the dot. It is the wind conditions at that dot that are being depicted in this station plot. The stick gives an indication of the wind direction, and one thing that it's important to remember is that there's an implied arrow coming out the other side of the wind barb, and in fact they used to be drawn that way, but as we got more stations and maps got more cluttered, they kind of dropped this arrow part. So if you remember that they used to draw an arrow through the station, it becomes a little more apparent why this indicates winds from the southwest through the station. And then the feathers on the back side of the arrow indicate the speed. And in this case, it depends on it. Some places it's knots or meters per second or miles per hour. We'll typically deal in in miles per hour. So what this would indicate would be 2 long barbs would be 10 plus 10 is 20, and a short bar would be 5. So this is winds of approximately 25 miles per hour from the southwest at this station. Okay, I'm going to jump in here because there's a point I needed to make, and that was what we call these winds. Winds from the southwest, we call them southwesterly winds. Southwesterly winds blow from the southwest. Northerly winds blow from the north. If you're a northern person, you're from the north. If you're a northerly wind, you're from the north. Some people will get cute and say southward, meaning north to south winds. Those people should probably be shot or jailed. The correct term is northerly winds from the north, southwesterly winds from the southwest, easterly winds from the east. The wind direction is talking about the origin of the winds or where the wind is coming from. Another topic in this week's material is precipitation processes. And so make sure you get familiar with how cloud droplets collect other cloud droplets and tiny droplets and generate precipitation. To be honest, we won't spend a great deal of time on this, but this is a really important and kind of specialized part of meteorology. In the field, the cloud physics people really examine the heck out of this, and knowing exactly how cloud droplets form is important, not just to the general meteorology and forecasting and understanding the weather, but a lot of the engineering and observing approaches that we use, like radar, are really helped out by knowing exactly what's going on with those droplets. So do spend some time in there, please. What other? Precip typing. So we had a couple examples of how different precip types can occur, and because this is January of 2012, Happy New Year, by the way, we'll go over some winter scenarios. You'll see this play out a lot. Almost everywhere, almost every day somewhere in the United States is dealing with rain and snow, and there'll be the band of mixed precipitation, and you'll always, if you wonder why do we go from green to this pink band to snow, here's kind of what's going on. So my son has 1 million Sharpies, and we're finally going to put those to use. So this is a hypothetical of the atmosphere. Okay, so we're going to go over 4 precipitation types: snow, freezing rain, snow, sleet, freezing rain, and then rain. These are the 4 major precipitation types that can occur during the winter. So what we have here is just a schematic. So this is the ground, and as we go up in the atmosphere, we're going to measure the temperature. And each one of these diagrams is going to go from left, it's going to be cold, to right is going to be warm, and we're going to draw a temperature trace on here as we go up. So everywhere to the left of this dotted line is going to be below freezing. Everything to the right of the dotted line is going to be above freezing, or warm. So warm in this context just means above freezing, warm enough to melt snowflakes. And so what happens is I'm going to draw, say, the temperature of the atmosphere going up, and in this scenario we'll keep the whole temperature trace, the whole temperature profile on the cold side of this freezing line. And what that means is snow or precipitation that generally starts up higher in the atmosphere as snowflakes falls through an atmosphere that is below freezing all the way from the precipitation origin to the ground. And so at no time will this atmosphere melt the snow. And so when the atmosphere looks like this from the ground up, as long as that temperature trace stays on the cold side of the freezing line, it's going to produce snow. So snow is, this is what a snow sounding would look like. All right, another scenario is, we'd not be able to do it that way. So another scenario would be, what happens if the atmosphere, all precipitation in the winter is generally going to start out as snow on the left side of this dotted line. What if it has a little warm nose and then a relatively deep and cold freezing layer at the surface? So what's going to happen in this scenario on the right here is we start out as snow below the freezing line or left of the freezing line in cold temperatures. So precipitation is going to fall as snow, and then it's going to encounter this little warm nose. It actually looks like a nose, and that's the melting layer or warm nose, and that's where snowflakes are melted. So once it falls through a piece of the atmosphere that is warmer than freezing, that snow not immediately, but very quickly melts, and we become raindrops or droplets in this scenario. But then it goes through a fairly deep and fairly cold layer near the surface, so it will refreeze before it hits the ground. And that is what produces ice pellets. So if you're in a winter weather situation and you get that pelleted icy kind of sleet, is exactly what it is. So this is a sleet sounding. And again, the difference between a snow sounding and a sleet sounding is a snow is on the cold side of the freezing line. It's always below freezing from the precip origin down to the surface. In a sleet scenario, we are cold and we have a melting layer, but then we have several hundreds of feet and very cold temperatures to help refreeze those drops that melted here. So down at the ground we would experience frozen precipitation. All right, this is very low tech. Another situation similar to sleet. In fact, it is one of the toughest forecasts in the business, is determining precip type between snow, sleet, freezing rain, and etc. Is, let's say again in the winter it is very much below freezing, high in the atmosphere at the origin of the precipitation, and we have a melting layer, and then we have a very small freezing layer or refreezing layer. So what happens in this scenario, much like the sleet scenario, the precipitation starts as snow. It falls through an atmosphere that has a warm nose, and that snow melts. It turns into droplets. Those droplets warm to whatever temperature they're falling through, or at least close. And then there's this very shallow sub-freezing layer near the surface. And what happens here is, even though the snowflakes melt in the melting layer, they don't have the time to refreeze before they start hitting objects on the ground. So they're actually very, very cold water when they strike the surface. Now everything that's down here, like people and power lines and trees and anything elevated off the surface of the earth, is going to be below freezing. So when those water droplets hit trees and power lines, it's going to refreeze at the surface and cause a glaze of ice. And if there's a lot of precipitation, it'll cause a giant, coating and caking of ice. So this is a freezing rain scenario. And freezing rain is different than sleet in that sleet drops and strikes the surface as a pellet and typically pretty harmlessly bounces off stuff. Freezing rain strikes the surface as a liquid and then almost immediately freezes. And it can accumulate on trees and on power lines, and these can be catastrophic storms in the winter. The energy industry, the electrical transmission and distribution networks can really get hammered by these things. It can cause billions of dollars of damage in just the electrical infrastructure, and the ecosystems can get hurt by freezing rain as well too. You bring a lot of tree limbs down. That's a shock to the system, for the natural systems. And then, of course, if you're walking around in this stuff, you can slip and fall. A lot of injuries, a lot of traffic accidents. So this is a nasty scenario. So this is freezing rain, and that is usually where you don't want to be. That's probably the least desirable scenario that you want. Finally, let's say you have a temperature profile where you start out as snow and you gradually warm as you get to the surface and you stay above freezing at the surface. Well, the snow melts, and even though it's winter, you're above freezing and you get very cold rain, which is, in the south, this is the most common type of winter precipitation. Those of us who live in the south, we see rain more often than we see the frozen stuff in the winter, because we don't spend a whole heck of a lot of time below freezing or for any length of time. So these are the different scenarios. Again, we'll flip through and apologize for the low-tech approach. But the warmest scenario is rain. That's liquid at the surface, and it stays liquid. It doesn't freeze to anything. It runs off just like a normal summer rain. The second warmest scenario is freezing rain. You have a warm nose and a very shallow refreezing layer. In fact, it's not a refreezing layer because the droplets don't have time to refreeze. They refreeze once they strike something, stick to it, and then coat it, causing all of those problems. The next scenario is sleet. It looks a lot like freezing rain when you look at the temperature profile, except that this refreezing layer is deeper and colder. And so the droplets that fall through here have the time and the temperature to refreeze before they hit the ground. And then the coldest scenario is snow. When you have snowflakes hitting the ground, that means that the temperature was below freezing from the point that they became precipitation all the way to the ground. So if you want to arrange these scenarios from cold to warm, snow's the coldest, then sleet, then freezing rain, and then rain itself. And those are the winter weather precipitation types. Hopefully explained using kitty markers and Sharpies, and I apologize for that, but we don't have a whole lot of high-tech production equipment here in my attic. The other one more point about precipitation typing is sleet is a pellet of ice that occurs during winter, and hail is also a piece of ice that occurs with thunderstorms, but these are very, very different in their origins. They're on the ground, they're a piece of frozen material. They pelt things, but their origins are vastly different. Sleet is a wintertime process, and you saw that the freezing layer was very close to the ground. Hail is a result of thunderstorms, and that is a result of warm, moist air being lifted very high into the atmosphere where it's cold, and the hailstone is actually formed very high in a storm as it's held up by an updraft. The freezing layer in the thunderstorm is well above ground, creates a large piece of ice. That ice eventually falls to the ground. Most of it survives the melting process. So major difference between sleet and hail. Sleet is a cold season phenomenon. The freezing layer very close to the ground. It actually freezes on the way down as it nears the ground. Hail is a warm season, or at least a warm season weather phenomenon, where the freezing occurs very high in the atmosphere as it is being held up by an updraft, and then it falls to the ground. Again, I would very much focus on these precipitation typing things and the concept of stability. Read it a few times. Email me if you have any questions, or post it to the forum. Good luck this week. I will be getting some assignments to your gradebook very soon. All right, thanks a lot. Bye-bye.